Thank you very much, Stefania, for the nice introduction. Thank you, everybody, for being here. Now, the situation seems calm and relaxing with respect to previous talks. Glad to be here for fourth time in a row, if I correctly remember, at the PyCon conference, and most of all, honored to give a talk for the second time in a row at the PyCon X. Little introduction of myself. I work at the Max Planck Computing and Data Facility, which is a computing center based in Munich, south of Germany, which belongs to the Max Planck Society. I mean, the institute belongs to the Max Planck Society, not the entire city of Munich. The Max Planck Society is a research entity, environment spread all around in Germany. And our role is to support, to collaborate with other Max Planck Institute in the sense to provide computational support for projects which demands high-performance computing and data storage. Today, I would like to walk you through some fundamentals of generating deep learning models in some popular deep learning frameworks like TensorFlow using Python, especially on large computing systems like the clusters we host at our institute. First of all, I have to apologize with you because unexpected, the screen doesn't fit very well with the slides. I'll try to do all my best scrolling down and giving you the opportunity to look clearly at the slides. The talk is structured as follows. First of all, I would like to give a very brief overview of deep learning, machine learning, or in general, artificial intelligence, especially in the context of high-performance computing. So talking a little bit about the software stack and especially the hardware required for such purposes. And then I would like to present the results we recently achieved in a collaboration project done with one of these Max Planck institutes in the field of neurosciences, neuroimaging, so the brain MRI images. So everybody now talks about, we have also seen the talk by Marco, we talk about machine learning, deep neural networks, deep convolutional neural networks, artificial intelligence, which sounds kind of buzzwords, and so on. In reality, the deep neural networks as mathematical algorithms attracted the attention of machine learning community since the 1980s. And until a few years ago, unfortunately, it was just reduced a kind of scientific curiosity. This is essentially because of two aspects: lack of the massive amount which is available nowadays, and especially for the computational power. On the other hand, nowadays, everybody says we are living in the big data era. 90% of the data available on the internet has been collected in just the last couple of years, and so on. So this aspect, combined with the rise of computational power, massive increase of computational power in the last years, has led deep learning towards the high-performance computing world in a point that both scenarios now are tightly coupled. What I mean is the availability of such powerful machines has allowed data scientists or researchers in general to exploit deep learning inherent parallelism. In a paper of 2018 by some researchers at the ETH in Zurich, they have analyzed research papers, 227 to be precise, in order to understand the trend of deep learning applications and the hardware or software stack used for such purposes. We see on the left-hand side plot the more and more use towards of GPUs as kind of a standard de facto hardware in order to run deep learning applications. On the right-hand side, the bar chart plot showed the fact that deep learning application moved more and more from single node towards multiple nodes. So the question is nowadays, how many nodes we want to use in order to run expensive, from the computational point of view, deep learning applications, and how we want to communicate, how the communication is between these multiple nodes. So in the end, a deep learning problem, a deep learning application is a supercomputing problem. We have also seen in the last couple of days that scalability is a key concept for achieving performances in deep learning. Think about, for instance, to the ImageNet datasets available. It's a couple or more terabytes of the data. And then think about how you want to store the weights of your model. Could be millions of parameters in bytes, could be something like 0.18 gigabytes, and you need to keep in memory when you train models, when you use to run your deep learning applications. So high performance is highly demanded in order to run deep learning applications. We are in a Python conference. The answer is easy. We love Python. We want to use Python. Actually, the question should be why using Python in larger computing systems. The productivity of languages Python has increased by leaps and bounds. Such performances, productivity benefit data scientists in all stages of their artificial intelligence experiments applications, from pre-processing data, running training, post-processing data, and analyzing results, interpretations, and so on. So in order to meet the needs of data scientists and the demand of getting high-performance solution, at MPCDF, at the Max Planck Computing Facility, on our machine, the major effort is to provide a software ecosystem which allows data scientists to keep going with their favorite tools. So Python, NumPy, scikit-learn, and so on. In scalable and hardware agnostic fashion. What I mean is the aim is to let people to run their favorite Python codes behind simple prototyping and scaling out to some large computing system, high-performance computing systems. We provide Python as a simple load according to Anaconda distribution. Before running any deep learning frameworks, on our machines there is a kind of hierarchical structures. You first need to load Anaconda, and then on top of an Anaconda you can load whatever favorite tools. The Python distribution we provide is highly optimized. It means that the NumPy, for instance, libraries are tightly coupled to the math kernel libraries provided by Intel. If you want, try by yourself, import NumPy, and then check by yourself if your NumPy library is tightly coupled with the Intel math kernel libraries. This provides you, guarantees you at least some gain in performances, which means you get high performances out of the box, or with simple, with no code, no change, or at least minimal changes in your code. If it's not, you should get some messages like that. Means you don't have NumPy linked to your performing library provided by Intel. As a deep learning framework, the main deep learning framework is TensorFlow, the framework we provide. Large communities behind TensorFlow, open sources. Nice Python API, so in principle easy to use. And Keras on top of TensorFlow. Actually, in Keras, you can either load a module Keras using TensorFlow on backend, or simply use the TensorFlow implementation API in Keras, like import tf.keras simply. But we don't simply provide TensorFlow and Keras or whatever deep learning framework. We provide optimized TensorFlow version, which means the TensorFlow at the CPU level are tightly connected to the Intel MKL-DNN, which means the math kernel libraries, deep neural networks libraries. And there is also another Intel library called Machine Learning Scaling Library, which provides a nice implementation of communication patterns inside deep learning applications. If you want, check by yourself if your TensorFlow is optimized with Intel, simply printing this simple Python command lines. You should get true if it's coupled with Intel MKL. So in this case, TensorFlow is high performance. It is faster than the normal TensorFlow you get from downloading from the web page. It's beyond the scope of this talk, but if for those of you interested, there is a section on TensorFlow web page, a best performance practice or performance guide, where TensorFlow teach you how to get the best performances linking TensorFlow with Intel MKL libraries, like tuning some parameter like inter.op_parallelism or intra.op_threads. Essentially, you tune this parameter to the number of physical cores in order to get the maximum benefit of your machine. We provide not only CPU optimized TensorFlow, but also GPU. GPUs are very powerful. So you get the CUDA, Deep Neural Networks library, and most important, you get the NCCL. Actually, NVIDIA people, they pronounce Nickel library, which provides the opportunity to pass from a single GPU in a multi-GPU, and most important, in a multi-GPU in multi-node fashion. I mean, you have many nodes, competing nodes, isolate each other, and with this library, you can run your distributed deep learning application communicating among all the nodes. That's very important because scalability still is key concept important for this kind of application. Simply try to make sure your TensorFlow is running and getting benefit of the GPUs, simply carrying the device on your machines. Now, for simplicity, you see printed just one GPU device 0. On our machine, each node is equipped with 2 volta GPUs. So in principle, you should get printed 2 GPUs, GPU 0, GPU 1. For screen reason, I've simply queried one GPU. So at the level of environment variable, you just export CUDA visible device is equal 0 or equal 1, and then you get printed which GPUs is actually used for runtime. And then you see we have a powerful NVIDIA Tesla Volta architectures, Volta 100, with 32 gigabytes of memory, one of the fastest data center or machine for data scientist application. So giving this brief overview of software stack and hardware stack, now I would like to share with you results that recently we achieved in collaboration with a Max Planck Institute called Human Brain and Cognitive Science, based in Leipzig, still Germany. A little disclaimer, I'm an astrophysicist by training. So I have no clue, or at least I had no clue before starting this project about neuroscience, neuroimaging, neuro whatever. So I try to do my best to simplify what's on the screen. What I've learned from colleagues based in Leipzig is that magnetoresonance imaging, in short MRI, is one of the best or the best instrument method in order to inspect the structures of the brain or any soft tissue like brain. This is because MRI images provide you with images with high contrast, high spatial resolution, with minimal or no health risk for the patient. For a quantitative analysis of MRI imaging, you need segmentation because localization, detection of pixels within the images is crucial for any further diagnosis. So, so far, the most knowledge about cortical structures of the brain is based on 2D slices or 2D sections. Most of the work, any expert in brain neuro? You? So you probably know a lot. So most of the work in the past has been done literally by hand labeling of these images, which requires a lot of work, amount of time, like weeks or so. Correct me if I'm wrong.
No, it's right.
Who is the?
It's right.
It's right. Okay, thank you. Thanks for the feedback. Okay. Okay. Nice to see the audience is with you. Okay. So in this field recently, deep learning-based methods gain a lot of interest and more and more applications because essentially this helps to automatize the process essentially, avoiding to introduce some artifacts and so some errors due to the manual labeling of this kind of images. And the goal was to try to segment thousands of these cells inside of such big volume, 3D volume, I will show you later, out of the brain structures with a minimum or not at all labeling effort. Let me clarify that this project has been done in collaboration, as I said, the Human Cognitive and Brain Science, and there has been also Intel collaboration in this sense, because two solutions have been proposed. The one that I'm going to talk about in the next is what is called parallel tile-based inference, and I'll explain the meaning of these sentences. And then there is an alternative, or let's say parallel solution provided by Intel for this specific scientific purpose. And let me clarify that essentially in machine learning or deep learning, it's kind of two steps. You train your model, well, then there is validation to tune your hyperparameters, and then there is the important next step, interference or interferencing, which means you want to test your model after training on a lot of data. And we have given our contribution just in this step. And I'll explain why. So essentially, segmentation is important because segmentation is labeling of images or pixels in 2D images, or what is called voxels for 3D structures, volumes. The kind of image we are dealing with is called TIFF images, tagged image file format. Normally, people dealing with deep learning, computer vision in Python, essentially, I guess the favorite Python library is the PILO library or PIL package. Wasn't helped, unfortunately. So I used the scikit image for image processing. A little dive into the structures of the volume. We are dealing with the image of 60-bit. So the range of the pixels values is from 0 to more than 60,500 and or so. And the shape is, well, grayscale images, height and width of 1080 times 1024 pixels. Seems a kind of standard format for this kind of scientific community. For a stack of 2,304 images, one on top of that. So this is kind of the volume we had to deal to make inference of this volume. You see the, well, you see, I hope you see, the scale of the volume. So imagine you have a lot of these 2D images stacked on top of each other. Seems impressive if you consider the numbers, but actually, sorry, actually in the laboratory, this corresponds to kind of a tiny stain of 1.12 millimeters times 1.2 millimeters times 2.4 millimeters of post-mortem human brain cortex. So such a tiny piece of material, human brain, but highly computational demanding. So, okay, normal rescaling of image and normalization, since we are dealing with the image 16-bit. This is a slight projection on the zeta plane, zeta equals 0, y times x. And you can see the granular, and this is a 2D projection, so but I hope you can see the granular and pyramidal structures of these cells inside this volume. So more than inferencing, the task, the deep learning task has been to identify, to detect the cell centroids of this spheroidal region, and then with advanced image techniques to reconstruct it, to delineate contours, boundaries of the structures inside the human brain. Okay, so explain the details of the neural networks the people in Leipzig have used for this kind of tasks goes behind of the purpose of the talk, but at least I would like to give you a schematic view of the network they have used. They've used the so-called mixed scale dense convolution neural network. In general, what the typical convolution neural networks, you have the input images, m rows times n columns times c channels. The purpose is to find a function which maps the input images through intermediate stages, the so-called features maps or layers, in order to then to get the output images of n prime times n prime c prime channels. The output dimension do not necessarily coincide with the input dimensions. And all these intermediate stages are connected each other through operations we know are called convolutional operation plus nonlinear functions like activation sigmoid, ReLU functions, and so on. However, in order to get more and more information on the image, people try to add more and more layers and some other operators like downscaling, upscaling operators. This is what is a typical kind of autoencoder. So the first half of the network is what is called encoder, and the second half of the network is called decoder. So compressing the images, the feature maps get shrinked and shrinked, and then decompressing in the second half of the networks. And typically the feature maps not only are, you pass through each stage, each feature maps through convolution operation, but you can connect also at different scales through the so-called skip connections. What is the main problem of this? This is more deep as neural networks with respect to the shallow schematic network above. The point is here, adding more and more layers, you had more and more parameters to be trained. There are some problems with the local minimum. Gradients gets too large. So the risk of overfitting is quite high, and the best practice to avoid overfitting is to add more and more data sets, which is not always feasible in the real life. So the main purpose of this author has been to, these two mathematicians, has been to introduce the so-called mixed scale network. And the purpose is to do more with less. Seems a political promise, but actually the idea is giving constraints of the amounts of data sets. We want to still have high accuracy on our prediction, on our results, with less amount of data. So they propose the mixed scale. The mixed scale is in the sense you have several scales. All these feature maps are connected to each other by the so-called dilated convolutions, which are kind of convolutions or using dilated filters. Dilated filters means they are non-zero at some distances, multiple of some factor, the dilation factors, distant from the center. Let me probably explain in another words. So classically, in this kind of network, what is key concept important? The receptive field. If you, for a moment, forget about pooling operations, you see that the receptive field is linearly increasing with the layers. So you have a quantity times L, the index of layers. And if you add more and more layers, this quantity, the receptive field gets higher and higher, okay? The point is, with the dilated convolution, you can get the same high receptive field, but using less layers and so less parameters. So this should be easier to train, keeping the same high accuracy. And then this gives the aspect of mixed scales, because the networks start learning large-scale information at very early stages of the training. And then densely connected, because the output, the final output, is not simply relying on the feature maps preceding the output, but all feature maps exchange information between each others. Okay, this is I'm running out of time, so this is a simple code, implementation code, a few lines of codes. Let me remind that one purpose of using this network is because it's easier. You don't need such incredible amount of data sets. And secondly, probably also equally important, it's quite general. The network is always the same kind, internally, always the same kind of operation. So the idea is to be general purposes, can be applied to different scientific tasks with minor changes of the code implementation. However, if the topology of the network is fine, there are some computational issues, especially the inference. Let me specify that they have implemented the training with TensorFlow on images. The images I've showed before, and making training on randomly selected small image patches of 96 cubed pixels. If you think about the other famous popular network used in this kind of brain image processing, the UNet, the UNet could be also get millions of parameters. Instead, this model size is quite cheap in this sense, let's say 100K parameters. On the other hand, at level of the inference, making simple estimation, we concluded that the computational power required was 16 petaflop. So peta, I don't know if you know what's the number, 10 to the 15. So you have to add 15 zero after 16. In terms of memory, what it was required 24 terabyte, not available on daily basis, I guess. The topology doesn't allow to be splitted because there is high data dependencies between different scales and so on. So in practice, the maximum size of volume portion that I could use and I could fit in the memory of GPU was 100 cubed pixels, 100 by 100 by 100. This is a kind of selection of the images. So what we have working on, and I'm going a bit faster, is the called inference strategy, tiling-based strategies. So the idea is to divide the entire cube in small cubes, and then let the network processes each of these small cube at a time, and then in the end reconstruct the final image. But the idea, okay, fine, but nobody guarantee the results is okay. The results are okay, because one thing is to make inference in one shot of the entire volume. Nobody a priori, I guess, guarantee you that if you look instead on small regions each times, you get the final results equal to the first case. So what I've done is make some preliminary test, and then I call the parent, child, and child over. I'm explaining the meaning of these words and comparing with the ground truth. So in the ground truth, first of all, there are 10,000 of cell centroids of interest that need to be detected. Okay. Then these are quite pixels, are tiny pixels, so not visible. In the 100 times 100 times 100, I found 9, I guess. In this particular test, I found 9 centroids that need to be identified. In order to visualize, I need to make a kind of spherical masks, and I'm using the radius of 5 pixels because the network uses a kernel filter of 5 times 5 times 5. So in order to be consistent, I have amplified, let's say, each cell centroids with a spherical max of radius 5. So these are the ground truths. For instance, in this selected volume, these are the 3 cell centroids that my network has to identify. Okay, so the first experiment has been done, okay, with 100 cube pixels, my poor GPU is still capable to run inference, and the results are consistent, so the network is giving what expected. The 3 cell centroids are correctly identified if I compare with the ground truths. The next experiment, unfortunately the image is scattered, the idea has been to divide the cube in so-called tiles. So the first experiment has been to divide each dimensions by 2. So in a cube you get 8 subcubes. Please follow the black borders, keeping no overlap. So simply 8 subcubes inside. And the experiment was like this. If I don't consider overlap between 2 adjacent tiles or cubes, I get several problems, some border errors, which are important. I mean, it's a several issue. If I keep overlap between 2 adjacent cubes, then I correctly reconstruct the cell centroids afterward. So the idea is now to make parallel and distributed what I've done locally on 100 cube pixels on a large cluster system. And simply, if I have my input volume, dimension specified before, then I divide it in some opportune subcubes and let my huge cluster processes independently on each of these subcubes, and getting the final output with the same image, with the same dimensions, and hopefully correct predictions. So, okay, I don't know if you are familiar with Slurm. Slurm is a standard de facto workload manager on high-performance computing systems. Essentially, if you want to run a for loop for job 0 to job n, instead of writing by yourself this for loop, Slurm make the loop for you. You just have to magically specify how many jobs in parallel you want to run, the portion of the data each of these jobs has to process, and then Slurm makes the job for you. I simply show the main idea of this. So essentially, I proceed tiling by tiling. This is a 2D projection, but imagine for the entire volume, and so on. Let me skip all these technical details. I'm running out of time. There is a 3D reconstruction. It just inverts the process of splitting the data. So once you are taking care, pay attention of the correct dimension and the order how you split the volume, then it's easy to reconstruct back the images. A lot of details. Here, the final results. So I have run 30 jobs in parallel using 15 computing nodes. Each computing node has 40 cores, CPU, Skylake architecture process. If you run in hyperthreading, that means you get 80 logical CPUs, and the final inference was made in a kind of an hour and a half. On the same machines equipped with the 2-volt GPUs, the final time was kind of 6 minutes, and so on. So a giant step forward in terms of time computation. The solution provided by Intel instead is called the OpenVINO, Open Source Visual Inference Neural Network Optimization. At the beginning, this solution has been decided to be a kind of inference at edge, like on small USB pen or camera detection and so on. But they realized that this kind of technology can be used also on large data centers and computing for computational intensive tasks like the one I have proposed. And they managed to make inference in one shot, so on the entire volume. This was their challenge, on a single Xeon node. However, the machine required 1.2 terabyte. Not everybody has this machine at home, I guess. But still, was a great improvement, and the inference was made in 41 minutes. Okay, simply I show the results. So this is, unfortunately, I cannot run a live demo with the visualizer of the image because I'm running out of memory with this laptop. This is a section of the data sets. You see the granular shapes and so on. On the right, you have the so-called ground truth. This is what I got by applying tiling approach. Seems reasonable. And this is what people from OpenVINO got. So specialists in the Leipzig said, we and OpenVINO, we are getting quite good agreement each other. So both solutions are fine. And yeah, and I hope I've convinced that high performance is key, fundamental for this kind of projects. And I thank you for your attention.
Thank you, Giuseppe. There was a lot of digest. Perhaps you can put up your contacts for further question. We run out of time for question, and I think you have time to digest all the slides and ask you. But thank you again. Take a stamp of that. You will be here around the conference for more questions. Okay. Okay. Thank you again.